Hey everyone, welcome to the Algorand Hackathon, to the Reach workshop. Big welcome to all of you. We have got Jay here from Reach. Welcome, Jay. Thank you so much for joining us. Steve-O, who is your kind of PM, is currently flying to Austin. Nice on him. He gets to go to Austin Consensus. But yeah, I'll be covering today. So I'll just be dropping a couple of links in the chat as we go. If you got any questions, just put them in the chat and Jay will answer them. I'll just kind of button while he's presenting. But yeah, Jay, over to you. Thank you.
Hey everyone, how you doing? Thanks for joining the Encode Club today. I wanted to give you kind of a preview of what we're going to be doing today and talk a little bit about who I am. So I'm the CTO and co-founder of Reach, which is a development platform that's one of Algorand's partners. I believe that you are all starting a hackathon, or you're working on a hackathon now, and Reach is a development platform and tool to help you with that. What I'm going to be doing today is talking a little bit about how to learn Reach, what Reach is, and showing you some sample programs to get you started. I could talk for 5 hours about this if you wanted to, so I'll have some things I plan on talking about, but if there are any questions at all as we're going, I would be happy to answer them. I'm going to be primarily sharing my screen, so I won't see what your comments are, so I'm going to rely on Jake to let me know, hey, there's a comment, then I'll go look over in the chat. I'm here in Austin at Consensus, and so the wonderful people at the Tommy Hilton let us borrow an empty room that doesn't have all of its lights installed. So that's where I am, if you're curious. And it's very exciting to be with you all now. So to start off with, as I mentioned, Reach is a blockchain development platform that makes it easier and smarter to develop blockchain applications. One of our main partners is Algorand. And when you write your program in Reach, you'll be able to use it on a variety of different chains. If you go to our documentation site, when you click on this Start Building in Reach, you'll get to this site right here. And I want to kind of walk you through what we're looking at. So the documentation for our language, so we're a unique programming language, is in the Language tab. There's also a front-end tab that talks about how to build front-end applications. And then there are tutorials. And so tutorials are the primary thing that we'll be talking about. And there's a first tutorial called the overview, which talks about what Reach does. And there's a long, and this is very, very short. And then there's a long tutorial called Rock, Paper, Scissors that walks through the development of a particular application. Now, I want to give you kind of the fast version of what is in all of this material. And if you're interested, you can go read more about it. So when you build a decentralized application, you're kind of building a few different components. You're building the smart contract. There's lots of attention in the world given to smart contracts. Smart contracts are programs that execute on blockchain virtual machines. So one way to think about what the blockchain provides is it provides this single computer that the whole world is collaboratively running and executing on. And so that single computer, it has memory, it has programs that it's running, and those programs, they don't do anything until someone sends them information. They're input-driven programs. And so every time a transaction is sent on the network, you can kind of think of that as like calling a function on one of the programs in this big giant computer. And so that's what the smart contract is. But now, of course, the people that send the messages into the smart contract, those are also important components of any decentralized application. So this would be, imagine that we're talking about an application that implements a loan system. So there's borrowers, there's lenders, there may be, administrators, there may be loan underwriters. There's a large variety of people who are all interacting with one another to facilitate this decentralized application. And each one of those are part of the program, or part of the dApp that you're designing. Now, most of the time when you learn about decentralized app development, all the attention is given on the smart contract, and these other participants are ignored in the discussion of the program. Reach is not like that. When you write a Reach program, you write the entire set of interactions between all of these participants, and from that, our sophisticated compiler derives what the smart contract must be to facilitate that interaction. And so when you look at a reach program, you're looking at a description about what all of those parties can do when they execute the program. And then from that source code, we can derive the smart contract, but we also derive programs that are the implementation of, say, the lender, the borrower, the underwriter, etc. And those are all programs that would otherwise be written manually in a traditional development scenario. Now, one of the things that's special about Reach is that in addition to helping you write this program at this higher level of abstraction, we also provide verification guarantees about what your program does. So, for example, a property that you would like to hold of pretty much all blockchain programs is that they don't try to spend money that they don't have. And so this property is called linearity. And so you essentially want to guarantee that every time you try to use a resource, you actually have that resource. And Reach enforces this property for you as part of the compilation process. So I feel like I've talked a lot about what Reach does, and I want to open up the covers and show you a little example. And I'm going to be walking through some of the components of the rock, paper, scissors example. I'm not going to talk about everything that's in rock, paper, scissors. I'm just going to talk about some of the big ideas. So right here, what I have open is a little, the example program, the start of the rock, paper, scissors program, and it shows you kind of the structure of a Reach program. I'm using the Vim editor. You can use whatever editor you'd like. We have a VS Code extension that is very convenient if you like VS Code. Over here on the left side of my screen, I have the actual Reach program. And over here on the right side of the screen, I have an automated test program that I've written in JavaScript. Reach's syntax is identical to JavaScript. We literally use an off-the-shelf JavaScript parser to make sure that we are obeying all of the rules of JavaScript so that JavaScript programmers are comfortable programming in Reach. When you use Reach, what you're doing is you're defining Reach applications. So we're defining a totally normal JavaScript variable that's called main, and it is a Reach application. Now, the rules of that Reach application are specified inside of these braces. And so right here, we're saying that this program is going to involve a participant named Alice and a participant named Bob. And one of the first things that you do in a Reach application is you specify who all the actors are that are involved in this program. Then once you're done initializing the program, you then actually write your program that describes the interactions between Alice and Bob. Of course, this program doesn't do anything, and so there's nothing more to say about that. But this is the structure of programs. You define who they involve, and then you describe what they do. Now over on the right-hand side of the screen, I have my JavaScript program. And my JavaScript program, in this case, is going to be a simple test scenario about running the program on the left. And I want to talk about each one of the components of it. So the first thing right here that we see is that we're importing a function called load standard library from our npm package. So Reach is a totally normal npm package that you can install in all of your favorite JavaScript infrastructures. So you can use Node directly if you're building a daemon. You can use Webpack if you're building something that will be deployed online. It works with Next.js and Vue and React and all of your favorite JavaScript frameworks. One of the things that we've done is we've made it so that by following totally normal JavaScript coding practices, we work with all existing JavaScript projects. Now this program over here is called index.rsh. That's our extension. And when you compile this program, it produces a JavaScript file called index.main.mjs. The word index is because this one was called index, and the word main is because this was the function, this was the application main, and MJS is the extension that's used for modular JavaScript. This is the new ECMA 5 standard for modules. And so we're going to import the compilation result of that program. Then what we do is we load the standard library. And now what we do is we form two test accounts. And notice that these test accounts, there's this parameter that's called starting balance. So one of the things that Reach does is it abstracts away all of the tedious busy work of deploying, especially testing your applications. And so you don't have to deal with passphrases for your developer account. You don't have to launch the network and then keep track of what they are. You can create new test accounts that are distinct from one another as you go and fill them with funds. But now each network that we support has different notions about the atomic units of the network. So for example, on Algorand, one algo is really a million microalgos, and that's 10 to the sixth. In contrast, on a network like Ethereum, every ETH is actually 10 to the 18 Wei, which is the smallest unit of Ethereum. And so what this function parse currency does is it abstracts the process of taking a user visible amount, like 100 algos, and turning that into microalgos. But if we were to run this on Ethereum, it would take 100 ETH and turn that into Wei. Then we establish two accounts, one for Alice and one for Bob. Then what we do is we create contract handles. Now notice that when we create the contract handle, we reference the account object for Alice, and we call the contract function, and we pass it backend. What is backend? That's the thing that got compiled by Reach. And we do the same for Bob, except with Bob, we also pass in the information about the contract that Alice deployed. Because what's going to happen in this program is that Alice is going to be the one who's responsible for launching this contract on the network. And so she's the one who initially knows about how to get to it. Then what we do is we use the JavaScript feature of promises, which is kind of like multi-threading. And we're going to run a thread for Alice, and we're going to run a thread for Bob. And then these two threads, we're going to wait until they're both done. This syntax right here, contract Alice.p, this is saying that we want to run the participant named Alice, and then we're going to have in between these two braces the different behavior of Alice, and the same over here for Bob. So this, what we've seen right here, is roughly the structure of almost every Reach application. You define your participants, you define test accounts, you connect to contracts, and then you run the programs. I want to pause for a moment and go back to the website and show you how you, the documentation and things like that for this. So this example that I just did, that I just walked you through, is this first example right here in the first section. So in our code, what we do, sorry, in our tutorials, we show the code that I just talked about, and we explain what each line does. Then we also do the same for the JavaScript code and show you that. Now, each one of these functions that we're looking at, there's hyperlinked documentation for them. So suppose that we are interested in the new test account. What we can do is we can click on new test account, and it'll go over here to the documentation for new test account. And all of the documentation for interacting with our standard library is on this page right here. And it talks about how, okay, well, the first thing you need to do is you need to load the standard library, then you can create an account handle. If you're deploying on a real network, then you're going to use what's called get default account to connect to a wallet. But if you're writing a test program, then you'll use new test account. Then what you can do is you can create a contract handle, which given an account, you can use the contract function and it will get a contract object. And then you can run participants. So you can do contract.p.alice, and that gives you access to one of the participants. There are a variety of other ways of interacting with contracts. So there are API functions, which are for calling, an asynchronous action on a contract. There's view functions, which are for reading information. There are events for following along what happens in the program. And we also provide convenient tools for doing things like launching tokens, which is a common activity in many programs. One of the main reasons that you want to use something like launch token is imagine that you're writing a program that is going to deploy it in the real world to use something like USDC. When your test programs, you can't use the actual USDC because it's a different network. And so what you do is you create your own version of USDC just for your test scenario. But then when you deploy it in the real world, you'll use the actual USDC. So generally, when you're thinking about the Reach documentation, you want to think about it as primarily being composed of this exhaustive reference about everything that the programming language provides. So for example, the code that we showed at the beginning that defined different participants, well, that is under the participant definition documentation. It talks about how, okay, there's a participant, you give its name, you have its interface, and there's similar things for defining APIs and views and whatnot. So let's return to the code. And this program, of course, doesn't do anything, and so we can't really see anything exciting happen. So let's open up a new program. that is a little bit further on in the in the design of this tutorial. And I'll talk about what the program does as we go. So our goal for our tutorial is to teach people about the ideas of blockchain programming without getting caught up in the details of any particular hard problem. So what do I mean by hard problem? Well, for example, a really popular thing among blockchain programs is to create what's called a decentralized exchange, or a DEX. And decentralized exchanges are this complicated economic idea where you're providing a facility for swapping currencies. And there's this sophisticated mathematical argument about why a good way to do that is to use something called the constant product formula. Now, if you go to many people teaching you about blockchain programming, they will often choose these popular examples to explain how those things work. But what that means is that you're not only learning about blockchain programming and the specific language you're using, but you're also having to learn about this particular economic idea and the particular financial formulas. And so something that computer science education has found over the long time, over its long history, is that it's very easy to teach people how to automate things that they already understand. And so what we tried to do in our documentation is choose a well-known problem that is the game of rock, paper, scissors. Most small kids know how to play rock, paper, scissors, but if you don't know what I'm referring to, the game of rock, paper, scissors, or Rochambeau is what it's called sometimes, is a game where um, two players secretly choose a hand to play. So they can play either the rock, the paper, or the scissors. And they secretly choose that and then reveal them at the same time. And then one of them wins because rock smashes scissors, scissors cuts paper, and paper covers rock. And so there's a very simple set of rules that determine who wins in any game of rock, paper, scissors.
Jay, there is a question. It says, how do you deploy to local block, testnet, or mainnet?
Sure. Yeah. So when I walk you through running this program, I'll make a comment about this. Just give me one moment, please. So in this example scenario, what we're trying to do is we're trying to make a program where two players, Alice and Bob, are going to compete with each other playing rock, paper, scissors, and they're going to wager some number of tokens. And whoever wins will take all the tokens. So I'm going to walk you through this program over here in a moment, but I just want to show you what it looks like when we run the program. I'm going to go down to my terminal and I'm going to type reach run. So reach is this command line tool that runs your, that can compile, run, execute, etc. your program. And we're just going to call that program, we're going to call it with the run. What happens is that what reach will do is it will look at what network you would like to be on. So in this case, I have it configured to use Algorand. It will start an Algorand testnet. Then it will build a Docker container that contains the code to execute reach. It will then run a special Docker node that will run the program, and then we'll see what the program did as we run it. One of the things that's special about Reach is that we use Docker to make it so that you don't have to install any software other than Docker and this very small script that knows how to configure Docker. This way you don't have to deal with any complicated dependencies or dealing with special versions of any language, and you don't have to deal with special versions of JavaScript or anything like that. Now, when we ran this program, it said that Alice played scissors, Bob accepted the wager of 5, Bob played rock, Bob saw the outcome was that Bob wins, Alice saw the outcome was that Bob wins, Alice went from having 100 units to 95-ish, and Bob went from having 100 units to 105-ish. They're not exactly 95 and 105 because they paid gas to run the programs. They paid fees. Now, this program ran on a testnet that we created behind the scenes. But if we want to connect to a particular network, then essentially what we do is in our JavaScript program, when we do load standard library, we can say load standard library and connect to testnet, or and connect to mainnet. Or you could do something like and use the user's wallet, and the wallet will actually decide what network they go to. So nothing changes about the program at all The only thing that happens is that we either change this one line or we change the environment variables when we run the program. Now, I'd like to walk you through what this program looks like so we can see how it did what it did. So this program, by the way, is it's 50 lines in the JavaScript, and it's 50 lines in the Reach program. So it'll be relatively easy to walk through this. So we define these two players, Alice and Bob, and both of them, they share what is called the player interact functions. So there's a function that's called getHand that can be called to find out what hand they want to play. There's a function that's called cOutcome that says who won. We saw these two programs run when it said Alice played scissors and Bob saw the outcome. Those were calling getHand and calling cOutcome. Now, Alice is special though because she knows what she wants to wager, and Bob is special because he has the ability to accept that wager. When you write a Reach program, once you define the participants, what you do is you describe what they do in the program. For example, what Alice does is she is going to look at the wager and the getHand functions, and then she's going to publish that information for all the world to see. And she's also going to pay into the contract the amount of her wager. One of the things that happens in blockchain is that anytime you share information on the chain, you're publishing it for all the world. And so that's what she does here. She publishes it for everybody. Then what happens is Bob, he now learns everything that was published. So he doesn't have to do any explicit action to follow what Alice did or follow the contract. That is an example of the kinds of things that's taken care of automatically by Reach. Everything that Alice publishes, Bob automatically learns. And so then he calls his accept wager function to find out if he wants to accept it. And if he does, then he then chooses his hand, publishes the hand, and pays the amount. Then what we do is we use some basic math to figure out who the winner is. And then we decide, given who the winner is, how much money will Alice get and how much money will Bob get. So if Alice wins, she gets 2 units of wager. If Bob wins, he gets 2. And if it's a tie, they return the wager back. And we transfer the funds that were originally given to the contract back to the end participants. And then when they're both done, then they both see what the outcome is. Notice that this program says nowhere in it, here's what the smart contract does. The smart contract code is derived automatically from this description about what the allowable behaviors of Alice and Bob are. Now, let's go over and look at the JavaScript code and see what happens over here. So we have the same preamble where we load the standard library and load the compiled code. We have the same preamble where we create 2 test accounts. But now what we do before that is that we define these helper functions to print out how much funds people have with a decimal point and get their balance. We figure out what the balance is for each account beforehand. Then we create those contract handles. Then what we do is we're going to define that common player object. So the common player object has these arrays that say what the hands and outcomes are. There's the getHand function, which will randomly choose the hand, and the cOutcome function, which will print out who won. Then we start up those 2 threads and wait for them, where Alice runs the common functions as Alice, and her wager is 5, and Bob runs the common functions as Bob, and prints out that he accepts the wager. And so that's all that we need to do. At the end, we grab the after balances, and then we just send a little printout message. Now, it may be a little bit unsatisfying to only see this output. It seems too easy. But if you would like to see what happens behind the scenes, we can run with reach debug set to yes. And this will show us all of the internal messages that are happening and being sent to the blockchain. So we can see here the actual transactions that are being sent and what addresses are being used and whatnot. So, and we can see things like, why is it that their balances are saying? Well, because there's, certain applications that were created behind the scenes and so on. That was a tie, it looks like. And notice that Bob spent slightly more money. And the reason that Bob spent slightly more money is that Alice, she doesn't have to pay for these 2 transfers. Bob does, so he pays slightly more. And something else that's exciting is that we could, if we wanted to, run on a different network. So we can just run reach connector mode set to ETH. And then now, rather than using the Algorand DevNet, it will start an Ethereum DevNet and use it. So here we're starting the DevNets, and it will run them, and roughly the same thing happens. The amounts are different because there's different amounts of gas that are spent on each network. Now, what I've just shown you is the code for the bets and wager chapter of the tutorial. The tutorial continues on to talk about a variety of different things. It talks about how to deal with timeouts and protocols. It talks about how to deal with trust and attacks. It talks about building an interactive application at the terminal as well as a web application. The majority of the content here is spent explaining how to build a React application that is a live version of the program that uses a wallet and has a user interface and that kind of thing. I won't go into those details now, but it's very straightforward, especially if you know how to use React already. Our goal with Reach is to make it so that a traditional Web 2 programmer can be a successful Web 3 engineer relatively fast. We find that people tend to take about a month to become really productive. Now, before I go to a different example, I just want to show you one other special thing about Reach, that thing that I talked about before, about the linearity and the way that it proves properties about your programs. So what I want to do is I want to insert an error into our program. And notice that in this part of the program, what we do is that if Alice wins, she gets 2 units of the wager, because Alice paid in a wager and Bob paid in a wager. What if I change this so that she actually gets 3 units of the wager? It is impossible for this program to run, because if this right here is 3, then for Alice would be 3, and it would be 3 times the wager we would be sending to Alice. And if the wager was 1, then that means it would be trying to send in 3 to Alice, but the contract only has 2. So if we deployed this program, then what that would do is Alice could start the program, send in her money, but there is no way that the money would be able to come out if she won. So she would be forced to lose, because that path through the program always has an error. Well, if we run this program, it's going to detect that it needs to be recompiled. And when it gets recompiled, it's going to show with an error. And the error says that on line 39, up here we can see on line 39, that's this line right here. On line 39, we tried to prove the theorem that the balance was sufficient for the transfer. And it's false. And it's false because you were trying to prove this theorem right here. This theorem says that this number is less than that number. Notice that this number on the right is the wager plus the wager. So that's how much money is in the account. So we were trying to prove that the amount that we were trying to spend is less than the wager plus the wager. And what could happen is that the wager could have been 1. Alice could have played 0. Remember, 0 is rock. And Bob could have played scissors, and rock beat scissors, so therefore Alice would have won. See, it says the outcome right here could have been 2, and 2 is Alice wins. And so if Alice won, then she would get 3, and 3 times the wager is not less than the wager plus the wager. And so what Reach does is it analyzes your program and finds errors through the potential of what your program could do, and warns you and will refuse to compile your program until you fix it.
Jay, sorry to interrupt. There's a question.
Sure.
Can you create testing or deployment scripts?
Yeah, so this program that I'm showing you on the right-hand side is a testing script. And so every example program in the tutorial, until we get to the interactive ones, they are test scripts. And when we get to the interactive one, that is an interactive application that's kind of like an interface to your program. And if you want to have a deployment script, then essentially what you want is you want a really, really trivial testing script. Because a testing script that launches and doesn't run any tests, well, that's what a deployment script is. So every example that you'll see on the documentation site is either showing you how to do a testing script, a deployment script, or the real actual application. Okay.
Perfect. Yeah, thanks.
So as I was saying, Reach will also detect the opposite problem. So the opposite problem is if when Alice wins, we only give her 1 unit of the wager. So if we run this program, we'll get a different error. And this error is going to say that, uh-oh, if we go to the end of your program on line 8, when the program is over, because the program, the Reach app is on line 8. So when we get to the end of the program, when it's all over, one of the things that we do is we try to prove the theorem that the balance is 0 at the application exit. But it could be that the wager was won, Alice played 0, Bob played 2. That means that Alice won, but we transferred out some funds. So what we did is we started with the wager plus the wager, and we subtracted how much Alice got, which is 1, and how much Bob got, which is 0. And we tried to prove that that was equal to 0, but it was false. And so what this shows is that Reach is protecting you against making a program that locks funds away forever. So when you program with Reach, you have this safety net behind the scenes that will guarantee that you don't have such mistakes. Now, as I mentioned, the rock, paper, scissors tutorial is a pedagogic example. No one cares about rock, paper, scissors. There's no rockpaperscissors.com. No one is launching their new Web3 startup being the best rock, paper, scissors dApp in the world. It's not something that is a relevant problem, but it's a useful way to talk about both the features of Reach and the elements of blockchain programming. What I wanted to do is, in the last half of our time together, is talk to you a little bit about what a real application looks like in practice. And this uses some of the more advanced features of Reach that are primarily in the reference material right now. So I'm going to go to another window. And over here, this program is an RSVP application. So let me talk about what that means. Imagine that we are going to run an event, say a hackathon. And what I would like to do is I would like to incentivize people to come to the event. But I don't want the event to be expensive. So I don't want to, because people value things that they buy. And so one way to make it so that people will come to it is make them pay $1,000. And if they pay $1,000, then they can come to my event. Well, I don't know about you, but, if I, buy something at, I don't know, at the taco stand, or I get French fries or something like that, and I paid $2 for it, even if I'm full by the time I'm halfway through the French fries, I'm gonna eat every single one of those French fries because I paid. And so I don't know if you're like me, but I really value things that I buy. Whereas things that are given to me for free, it's harder to value them. So something that is really common in the Web3 world is to have staking systems for events. So how a staking system works is you register for the event and you have to put up some money. So let's imagine that you have to put up $10. And when you register the event, you pay in $10, then you do the event, and if you actually show up for the event, you get your $10 back. This has a nice balance between having a free event, which is easy for people to come to, and a paid event, which incentivizes people to come. Because if you don't go to the event, then you don't get your money back. So for people who go, it's free, and people have to pay, so they are incentivized to actually show up. So what we want to do is we're going to build an application like that. What I'm going to do is talk first about what it looks like when this program runs. And then from there, we'll go into the actual code. So I'm running an example version of this program on the Algorand network. And how it works is it says that there's going to be these 5 accounts that are all going to RSVP for the event. Then what we're going to do is we're going to have these 3 check in for the event. Then we're going to have this one check in for the event. And then we're going to have this one check in. Actually, this one that says that they errored. So this one isn't, they're going to try to check in, but they're going to fail. This one's going to try to RSVP twice, and that's going to fail. This one is going to try to check in, but they are also going to fail. And then we're going to have this one check in, and then this one's going to check in twice. And then we're going to wait for the deadline. And then once the time is up, we're going to go look and see how much money people have left. And one of the things that we see is that people who who RSVP'd and registered and checked in, they have roughly the same funds that they started with. They have 99. People who didn't interact with the program at all, they haven't changed at all. Notice that this person tried to check in, but they never RSVP'd, and so that's why nothing happened. And then someone like L5UA, they did RSVP, but they tried to check in and it failed, and so they lost their funds. And then this account, XQWA, they're the ones who ran the event, and so they got the funds from everybody who didn't check in. So this is what it looks like to do this RSVP. This is an example of a testing script that we use to make sure that our program does what we expect it to. What I want to do now is show you what the testing script looks like. And then after we look at the testing script, then we'll look at the actual program. So we load the standard library, we create the deployer account, we figure out how long we want it to run, and we have it run a different amount of time depending on the connector. So this says that when we connect to the conflicts network, we let it take longer. Then what we're going to do is we're going to deploy the account. We're going to deploy the program. This right here, if you were to build a deployment script, it would just be this part of the program, and you would just leave everything else off because the rest of the part of the program is testing. So this right here is that example of a deployment script. In it, we say that the cost is going to be 25. Then what we're going to do is we're going to create 5 test accounts. And this right here just defines a little helper function for dealing with calls that we think are going to error. This just defines some helper functions for connecting to the contract as one of the users, for RSVPing. So to RSVP, we call the attendee I will go function. For doing a check-in, we call the check-in they came function. And then what we do is we just write this little test scenario where where 0, 1, 2, and 4 RSVP, and then the 4th tries to RSVP again and it fails because you can't RSVP twice. Then 4 checks in, 0 checks in, and then 3 tries to check in, but it fails because they never RSVP'd. And then we do a incorrect check-in, where someone tries to check in who is not the runner of the event. And so that fails. Then we have number 2 check-in, and then they try to check in again, and that fails. And then we wait for the deadline. We call the times up function, which allows the deployer to get their money back. And then we go see who won. So this right here is an example test scenario. You can kind of think of this as like a little SDK for working with our program. And that's how we get the program. Now, I've sort of walked you through this backwards, where we've seen how it ran, we've seen what the example test script looks like. And notice that our test script for this scenario is only 75 lines long. And we could, of course, write a variety of different bodies of this test, try different scenarios of different patterns of RSVPing and checking in or whatnot. But now let's dig into the details and actually see the reach program. So the reach program is 63 lines long. It's actually shorter than the RSVP program. Not the RSVP program I showed you, but the RSVP program, it's shorter than the rock, paper, scissors program, but not the one I showed you. It's shorter than the rock, paper, scissors program. That's the final version. And let's walk through the program from beginning to end. The first thing that we do is we define a participant named the admin who knows what the price is, what the deadline is, and they have a function that they call when the contract is ready to go. Then we have an API for attendees. An API is like a participant in that it is a thing that can interact with your program, but unlike a participant, it doesn't follow every single action of the program, and its state is not synchronized. So it's basically a way of sending information in, but it can't get information out except through the return. Then we have a separate API for checking in. In this, there's a function that's called, with the attendee, there's a function called I will go. With check-in, there's a function called they came, and another function called time's up. Once we are done defining all of the participants, we then initialize the program, and now we're ready to go. What the deployer does is they reveal to the world the price and the deadline. So they publish the price and they publish the deadline. Then what we do is we commit the program, and we say that we're ready to go. Once we're ready to go, then what we're going to do is we're going to figure out what block is the deadline for having things run. We're then going to define a complex data structure called a set, and the set is going to be all the people who RSVP'd. we're then going to use a feature that's called parallel reduce. And what parallel reduce does is it computes a value by repeatedly running the same code over and over and over again. So it's going to compute the values keep going and how many. And keep going is going to start off as true, and how many is going to start off as 0. As we're computing these values over and over and over again, we're going to record information about them that must always be true. So we're going to know that at all times, the balance of our program is going to be equal to how many times the price. Now, no money has been sent in, and how many is 0. So that means that the balance is equal to 0 right now. We're also going to have the invariant that the size of the RSVP set is equal to how many. So it's going to be perfectly the same size as how many people are going. We're going to keep running, computing this value while keep going is true. And the different actions that can happen during the computation of this value are I will go and they came. So I will go, how it works is we first check to see that the person is not a member of the RSVP set. Because if they are a member, then that means that they've already RSVP'd and that we won't let them come a second time. They are going to pay in the price. This value right here is how much money it costs to run this function. We're going to return true, insert them into the set, and then we're going to return the new values of keep going and how many. Keep going stays where it was before, and how many gets incremented by 1. Notice that because the price was paid in and how many went up by 1, and we inserted, that means that we've maintained our invariant. The size went up. That's why we do the +1 here. And the price went in, which is why the new balance is maintained. Now there's also the they came function. So the they came function is going to take an argument called who did it. We have to make sure that this can only be called by the deployer. We then have to make sure that the person being checked in already did RSVP. It doesn't cost anything to call this function, so that's why there's a 0 right there. We transfer the price back to the person and remove them from the set, which means that we need to decrement how many to maintain the invariant on the balance and on the size. Finally, the program can time out when we reach the deadline. And when we reach the deadline, the times up function can be called, where we return false to keep going, and how many doesn't change. Now, when we're done with this, we continue to the end of the program, and we have the leftovers. And the leftovers is equal to how many, and we transfer however many leftovers there were, units of price, to the deployer. And now the program is over, and all of the funds are returned to the deployer. This is a real interesting program that people use all of the time for running events in the Web3 space. And when I originally wrote this program, I wrote it in about, I don't know, maybe 25 minutes with the test suite. And then there's, in our repository, there's a user interface for this program as well. So this is what it looks like to use Reach. When you use Reach, you can define the participants in a program. You define what the allowable behavior is. Reach automatically verifies that that behavior is correct. And we provide a simple library for building test, deployment, and interaction tools, as well as the actual deployment and testing process. So running an example is as simple as writing Reach run and watching it happen. Our goal with Reach is to drastically lower the barrier to entry into getting into blockchain so that anybody who is a competent Web 2 engineer can build amazing Web 3 applications, and they can use their skills for the interesting and hard parts of building businesses and companies, and that's finding out what consumers want and need and providing it for them. Everything that we do at Reach is backed up by the formal verification guarantees to increase the safety and security of Reach programs for Reach consumers and put developers at ease with what they need to do. When you use Reach, you don't need to learn about the low-level details of whatever network you're on, whether that's an Algorand or Ethereum or one of the other networks. And we think that one of the best networks to build on is Algorand because they have the lowest transaction fees, the highest throughput, the highest performance network, and one of the most stable networks as well, in addition to all the other amazing things about Algorand, like the amazing ecosystem and the way that they have the valuable property of carbon neutrality in their green chain. So I'm very happy now to, answer any questions that you have about either Reach or blockchain development in general, or Algorand as well. I'm going to take off my screen sharing for a moment, but I can turn it back on at any moment if you need to.
Lovely. Thank you so much, Jay. Yeah, the floor is open for any questions. Feel free to either ping them in the chat or you can ask in person as well. Yeah, over to the floor.
Right, it says, what would be a dApp, if any, that can't be built or you wouldn't recommend to build with Reach? So our goal with Reach is to be able to build the vast majority of all applications. However, there will always be some things that you won't be able to build with Reach because you'll need to depend on extremely low-level details about how a particular chain works. So an example of this would be something like, imagine that you were trying to make, I don't know, like an optimistic roll-up engine for Ethereum. Something like that, I think, would be a bad thing to write with Reach, because one of the things that needs to do is it needs to perfectly simulate the EVM environment in the rollup engine. And so that means that you need to observe low-level details about the particular chain that you're on and expose those to the data of the programs that are running. And so one way you can kind of think about this is that if you think about traditional programming, it's kind of the question is, what programs wouldn't you write in C or JavaScript or Python? Well, you wouldn't write something like a kernel driver, like a device driver, because a device driver needs to know exactly what is in some particular hardware register that is the I/O port to the device that you're interacting with. That's the sort of low-level detail that Reach deliberately does not expose. Right now, basically every feature of a network like Algorand is exposed inside of Reach. There's one category of interesting thing that Algorand provides that we don't use in the Reach compilation, and that's something called a logic signature. So one of the things that Algorand provides is they provide stateful applications that are like Ethereum contracts, and those are called applications or stateful contracts on Algorand. Algorand also provides a special kind of stateless contract, where this is a contract that gets launched and it has no way of recording any memory. And because it has no memory, that means that it's extremely limited in what it can do, but there are some things that it can do. And one of the things that's special about a logic signature or a stateless contract is that if you can fit your problem as a logic signature, then you now can pay less. There are a variety of consequences of choosing that, but that's an example of something that Reach doesn't support. Now, that's sort of a technological thing that Reach doesn't provide access to, but that's not really the same thing as the question, which is that what is a dApp that we wouldn't do? And my question is, my answer has been about like the tech that is not exposed. I don't think that there's any application that people are thinking about right now that you couldn't build with Reach, because although there are those low-level things, those are not actually needed for the traditional applications that people care about. So, for example, when you are building, like, I'm highly skeptical that Zoom or Instagram or TikTok or all of your favorite applications include low-level assembly routines. Maybe actually Zoom might have a little bit of assembly routines because they're going to call some media playing library, and that's going to use some low-level routines on the in the back end of like the movie decoding engine or something like that. But the actual main thing that like the Zoom company made, I don't think that a single person at Zoom knows or writes assembly. And our position is that the dApp world is going to be very similar to the normal world, where most people don't learn assembly and they don't write low-level features. So in summary, the answer is yes, there are things that Reach doesn't expose, but we don't think that those things are actually used by real dApps.
Perfect. Thank you so much.
There's another question that says, how could I convert a teal program to Reach? The best way to convert your teal program to Reach is to throw it away and then think about what you want your program to do and then write it in Reach. So as an example, this RSVP program that we just looked at, when we compile that program to Teal. The program is 722 lines of code long. So that's 63 lines became 722. It's pretty typical for Reach programs to be 10, 20, 30 times smaller than the corresponding Teal program. Because, Teal is a low-level assembly language that is not designed for people to think about what they want their program to actually do. It's all about implementing the mechanisms of doing that. And that is actually one of the reasons why Algorand is so fast and performant, because it has such an amazing and fast virtual machine. And so when you are programming directly in Teal, you're having to deal with lots of representation challenges that stress how difficult things are. So probably the thing that you want to think about is when you made that original Teal program, what did you want that program to do? And I think that most times it's going to be very easy to take that same program and turn it into a couple dozen lines of Reach code.
Perfect. Thank you. Are there any more questions? Or can Jay go enjoy his time in Austin? Yeah, we will. Oh, there, Caleb gave you a thumbs up, so I'm sure that means you're free to go. No, we'll call it there. Jay, thank you so much. That was really, really cool. All the best with your time in Austin, and all the best with Reach and the future. Yeah, and happy to have your workshop like this on the Algorand Hackathon. So thank you so much.
Yeah, and please visit our documentation and website at reach.sh.
Yeah, someone dropped it earlier. I'll re-drop it there.
Yeah, and we also have a Discord community of people who are Reach developers who are working together to build a variety of applications. And something that's special about that community is that it's people dedicated to building amazing dApps, regardless of what network they want to deploy them on. So if you join in that community, you'll be able to talk to Algorand devs, Conflux devs, Ethereum devs, and all work together building amazing things. And I'm excited to see what you can all do in this hackathon. Thank you so much, Encode, for having us here.
Absolutely lovely. Enjoy. Thank you so much, Jay. Cheers, and thanks to all the hackers that were here. Enjoy your program. Bye.
Hi, everyone.